Dr. Abdul Hamid. Today we are going to see the elective 5B paper, in which we are going to be study the unit 12, that is measurement techniques. So in this measurements techniques, today we are going to be study about the X-ray diffraction and scanning electron microscopy and spectrophotometer. Okay, about all these we are going to be studying now. So here we are going to be see after going through this chapter, we'll be knowing about the X-ray diffraction techniques and as well as the scanning electron microscope technique, and also the spectrophotometer we'll be knowing about. So if you consider this X-ray diffraction, so this X-ray diffraction technique is mainly utilized to analyze the structure of materials in the atomic level. Okay, in the atomic level, if you want to know the size or if you want to know mainly the phase identification. Suppose if you take any crystalline material, if you take in case of the crystalline material, we will be knowing the phase identification and also to know the information on unit cell dimensions also. So with the help of this X-ray diffraction, we can get the information of the unit cell dimensions we can get, and as well as we will be knowing the phase identification. Even this XRD is also used to study the amorphous materials, which are non-crystalline materials we have. So we'll be knowing the amorphous nature of the material with the help of this XRD also. Okay. So generally these X-rays are having the wavelengths around 0.01 to 10 nanometers range they are going to be have. So when the X-rays scatter from a substance with the structure, from a substance with a structure, so interference takes place, and which results the higher and lower intensities. With the help of that, we will be knowing the structure of the material and all those things. And if you go for this microscope, so microscopes are the instruments which are designed to produce the images of the small objects which are unable to see with your eyes, which are having a very smaller in size of the order of nanometers. You'll be knowing the size of that. That is what the you have about XRD and SIM, which will be knowing. Now we'll see what is XR, how XRD will be take place, the principle of the XRD and R will be knowing. So here we'll be studying about the X-ray diffraction. Okay. So we will be calling it as a XRD. So with the help of this diffraction, the geometry of molecules can be known with the help of these X-rays. So this XRD technique, if you take it, is based on the elastic structure of X-rays you have. So when X-rays are passing through the atoms, that is when the X-rays are moving through the atoms, the three-dimensional arrangement, regular three-dimensional arrangements in a crystal, and as well as any defects that can be known. So most of the X-rays, what will happen means when they are passing through this what we call atoms, these X-rays will be undergoing some destructive interference with each other. Some of the X-rays are undergoing some destructive interference with each other, and these X-rays will cancel each other. But some X-rays which are moving in some other directions, they will be undergoing what we call interference constructively, and they will reinforce each other. Okay, they will be reinforce each other. That means when the X-rays are passing through any atom, which is a three-dimensional arrangement, whichever we have. So in that, if they are going, some of the X-rays will be destructively interfere each other, and they cancel each other, and some of the X-rays which are moving in some other direction, they will interfere constructively, and they reinforce each other. The reinforced diffracted X-rays, okay, the reinforced diffracted X-rays that produces characteristic X-ray diffraction pattern, which is used for the crystal structure determination. So if you want to determine the crystal structure, okay, if you want to determine the crystal structure, so the X-rays which they are going to be reinforced, that means they form this constructive interference. With the help of that constructive interference and the reinforce of these X-rays will give the what we call which can be helpful in studying the crystals structural determination, which will be helpful in the studying the crystal structure determination. So this this was initially given by the scientist Bragg. So we called it as a Bragg's law. So Bragg has been given this diffraction pattern, how it will takes place when the X-rays are moving in the what we call atoms. Okay. So here we will see how the X-rays, if you take a crystal, so this is the distance between these planes. So D is the distance between this plane and this D is another distance. So here a X-ray which is incidenting onto the plane, it will reflect in this direction. To say that A, B is the incident ray and B, C is the diffracted ray here. Okay, so it is incidenting with an angle theta here, and it is diffracting with angle theta. And another ray, say that A dash and B dash, and it is coming out with the diffracted ray as B dash, C dash. So these are the diffracted ray, and these are the incident rays, A and A dash. That is AB and A dash B dash as the incident X-rays, and BC and B dash C dash are the diffracted rays. So if we extend this normal, okay, so this is at point P, it is touching. So this one, if you extend onto this as normal at Q, okay. So this is atomic scale crystal lattice planes you have. Understand? So in this, a beam of monochromatic X-rays which are falling onto a crystal at certain incident angle. When a beam of monochromatic X-rays falls on a crystal at certain incident angles, intense reflected X-rays are produced when the wavelength of scattered X-rays interfere constructively. Okay. So to produce interference constructively, the difference in the travel path must be equal to the integer multiples of the wavelengths. Okay. So to produce the interference pattern constructively, the difference in the travel path, okay, the difference in the travel path must be equal to integer multiples of the wavelength. That is the principle which is involved here. When this constructive interference occurs, a diffracted beam of X-rays will be leaving the crystal at an angle equal to that of the incident. Okay, so these incident X-rays which are leaving from this are at an angle theta, which is same as the incident angle. Okay, so here if you see in particular, here we have taken a AB is the incident ray, okay, X-ray that is. AB is the incident X-ray, so which is reflected at B in the direction BC, okay, in the direction BC from this plane. So AB is the incident X-ray, which is reflecting as BC from the plane. Okay. So another X-ray we have taken here. Another X-ray. This X-ray is A dash B dash, which is incidenting at certain angle. Okay, A dash B dash. Another ray A dash B dash is incidenting certain angle, and it is reflecting at another atom B dash in the direction B dash C dash here. Okay, B dash C dash. So here we will take the two perpendiculars which are drawn. BP is one perpendicular, BQ is another perpendicular, which are drawn from B to A dash B dash and B to Q B dash and C dash. So this is the incident and reflected rays respectively. So now we'll take the path difference between these two rays. The path difference between these two rays. The path difference between these two rays is given by P B dash plus B dash Q. Okay. P B dash B dash Q. This is the path difference we are going to take. So when this path difference is a whole wavelength lambda or multiples of the whole wavelength, that is n lambda, then the two rays will reinforce each other and they produce intense spot. That is, by adding up, they produce the intense spot, and the condition is given by this PB dash is equals to B dash Q. Okay, this PB dash B dash Q path difference is equals to 2D sine theta. Okay, 2D sine theta. This 2D sine theta, this 2D sine theta should equals to n lambda. This 2D sine theta should equals to n lambda, where n is the 1, 2, 3, and so on. N takes the values like 1, 2, 3, and so on. This 2D sine theta is equals to n lambda is known as Bragg's law, which is known as Bragg's law. 2D sine theta is equals to n lambda is known as what Bragg's law we are going to become. So this is the relationship between the wavelength of the incident X-rays, comma, angle of incident, and spacing between the crystal lattice planes of atoms, which is known as Bragg's law, which mathematically we will write it as 2D sine theta is equals to n lambda you have. Okay. So this is what a Bragg's law. So this X-ray diffraction pattern can be done with the experiment. So we have different types of experimental methods are there to perform this X-ray diffraction. Okay, to study the crystal structure of the any material. Okay, so with the help of this X-ray diffraction, mainly what we can find is we can find the grain size Okay, we can find the grain size, or we can call it as what, crystal size. With the help of this X-ray diffraction, we can find the grain size or crystal size. We can find out, and we can be knowing the orientation of the crystal. Orientation of the crystal we'll be knowing, and as well as the any strain will be present inside the crystal. That strain also will be knowing. So that means presence of strain inside the crystal will be knowing. Presence of a strain inside the crystal will be knowing, and as well as if any impurity is present in the crystal, we'll be knowing. That is uh, presence of impurities. Okay, presence of impurities. So all these will be knowing with the help of this X-ray diffraction method. We will be knowing the grain size or crystal size with the help of this X-ray diffraction, or orientation of the crystal we'll be knowing, as well as the if any strain is present inside a material, that is a crystal, we'll be knowing, as well as the if any impurity is present, that also will be knowing with the help of these what we call X-ray diffraction. So if you see, there are some methods to get this X-ray diffraction. So there are mainly three methods are there. There are mainly three methods, three main experimental methods. Experimental methods are there. There are three main experimental methods are there for this X-ray diffraction with the crystal structure can be analyzed. What are those means? First one is Lave method. Okay, Lave method. This is for single crystal. This is for single crystal, and we have the powder method. Powder method. This is for polycrystalline. This is for polycrystalline powder, and the third one we have is rotating crystal method. Another one is rotating crystal method. So with the help of this, we will be knowing the single crystal. For a single crystal, we'll use this rotating crystal method. So these are the three main experimental methods are there to perform this X-ray diffraction. Okay. So we are not going into detail about this laser powder or rotating method, but what uh, we can find with the help of XRD, we'll be knowing that. And if you see the applications of this X-ray diffraction nowadays, so X-ray diffraction, if you take this Lave method, so with the help of this Lave method, which is used for mounting the single crystal in a precisely known orientation. It is useful for study of crystal symmetry, mainly this Lave method if you take. So with the help of this, we'll be studying the crystal symmetry, about the crystal symmetry you will be knowing. Second one, if you take, which we have is powder method. So this X-ray powder diffraction method is having so many applications. That means much applications than this Laves method you have. So with the help of this what you call X-ray powder diffraction, it can be used to find out the study of D-spacing. Okay, so it is used to find out the study of D-spacing. D-spacing. Okay, and with the help of this, if a mixture is used to for the study, measure the relative intensities as well as the relative concentration of each component can be obtained. That is also one application is there with the help of this X-ray powder diffraction, and also with the help of this we can be knowing what we call particle size. Okay, we can determine the particle size with the help of this powder method. Next, we can able to find out the what we call with the help of rotating crystal method. If you take, it can be used to align the crystals and measure the lattice parameters and determine the crystal structure. Okay, that are the those are the applications which are there with the help of different methods, whichever we have for X-ray diffraction. Okay, so now we'll be moving to know about this scanning electron microscope. So here we're studying about this. Next one is scanning electron microscope. Scanning electron microscope. So usually we'll call it as a scanning electron microscope. Only about this we'll study. But before going into detail about the scanning electron microscope, we should know that there are two main types of electron microscopes are there. So means one of this is the scanning electron microscope. One we have is a TEM, which we will be calling it as a transmission electron microscope. Transmission electron microscope is one type of electron microscope. Another one is which we are studying about. This is SEM, that is a scanning electron microscope. These are the main two types of the microscopes which we have. If you see about the SEM, so in this SEM, mainly this will be works with the help of the secondary electrons which are produced in the specimen are detected to generate the image here. Okay, so the main thing that is the image of a specimen can be taken by the secondary electrons which are produced by the specimen. So these are detected, and you can take the what we call image of specimen. And whereas if you go for TEM, that is a transmission electron microscope, so the TEM image is generated by the electrons that have transmitted through the specimen. Okay, so the SEM image is taken with the help of the secondary electrons produced by the specimen, and the TEM image is generated by the electrons that have transmitted through the specimen. Okay, this is what how the SEM and TEM will work actually, means the basic principle how the image can be recorded. Okay, so if you take the SEM here, which we are studying in detail, the SEM will scans the focused electron beam over a surface to create an image. Okay, so the electrons in the beam interact with the sample Okay, the electrons will be interacting with the sample, and they will be producing some various types of the signals they will be producing, which can be used to obtain the information about the surface topography and the composition of that material. Okay, so when the electron beam is hitting the sample, okay, when the electron beam is hitting the sample surface, it interact with the atoms in that sample. As a result, some of the electrons will be bounced back, means some of the electrons will be coming back from the sample, and some of them will be moving into the what we call the sample, and they will be displaced through that atom. Okay, um, that will be coming out of the sample as secondary electrons. Okay, secondary electrons, and some X-rays will be produced, and as well as the some heat can be produced with the help of this interaction. That means when the electron beam is hitting the sample, okay, when they are interacting with the atoms in that sample, which will result some of the electrons will be coming back, which will be calling it as a scattered electrons, and some of them will be moving into the atom and they'll displace electrons that will be come out of the sample, means the electrons which are interacting with the atoms, and some of them are coming out of the, some of them is backed, which we'll be calling it as a back scattered electron, and some of the electrons will be displacing through that atom and will be coming out, which we'll be calling it as a secondary electrons. And some X-rays are produced, some light or heat can be result from these interactions. So these many things will be happening when the electrons or fast moving electron beam is hitting the surface of the sample. So the generally the energy which is dissipated from the sample is in the form of heat. Okay, and the electrons which are coming out the material, they'll produce the what we call SEM image actually. Okay, which are coming out from the, they'll be producing the image. So now we'll see the what we call the schematic representation of the SEM. So here I'll show the picture, that is a block diagram of the SEM. I'll show. 1 minute. I'll show this image. Right. So this is what the schematic representation of SEM. So in this, we will have initially the electron gun. Okay, so I'll 1 minute. So here, initially, here, the electrons, right. So from here, the electrons are generated with the help of this electron gun actually. This is electron gun. So these generated electrons, how they are generating means these are emitted when their thermal energy overcomes the work function of the source material. Work function of the source material they'll generate. So this is how the electrons are generated, and these electrons are streamed with the help of a condenser lens. So which we call it as a first condenser lens. So this is a first condenser lens. Okay. So 1 minute. Right. So here, so this is the electron gun which is producing the, this is electron gun which is producing the electrons, and these after production of this what we call electrons from this electron gun, when it is overcoming its work function, and these are streamlined, the electrons are streamed in this through this first condenser lens. So it works in conjunction with the condenser aperture. So here we have a condenser aperture here. This is what condenser aperture, and they will be passing the electrons. Actually, the condenser aperture, what it will do means it will eliminate the high angled electrons. It will eliminate the high angled electrons from the beam. And we have another second condenser lens is there. So through this second condenser lens, which forms the electrons into a thin light coherent beam here. Okay, thin light coherent beam here in this manner. Okay, in this manner, and these will be passing through this objective aperture. This is what these will be passing through this objective aperture, which further eliminates the high angled electrons from the beam. After passing through this aperture, that is through the objective aperture, the scanning electron microscope lens system, which is consisting of scanning coils here, which acts as a electrostatic lens, okay, which acts as an electrostatic lens, which scans and sweeps the beam of grid fashion. That means again, the beam in the grid fashion it is going, and it is going to be passed through this object lens. They are going to be passed through this objective lens. After passing through this objective lens, they will be focusing the scanning beam to hit the specimen or sample. They will be hitting the specimen or sample at this point. So this is how the electrons will be produced, and these electrons will be managed to hit finally the specimen S here at this point. When this beam of electrons are hitting or striking the sample, it will be the interaction will occur here at this point. When the beam of electrons will be striking the sample, the interaction will take place. So before the beam moves to the next point. The instrument measures various interactions which are taking place inside the sample, counts the number of interactions, and displays as a pixel in the CRT tube that is on the screen. The intensity of display is determined by the interaction number. More interaction, if it is taking place, it will gives a brighter pixel. When the more interaction taking place, it will gives a brighter pixel. So the process is repeated until the grid scan is finished and repeated. Okay. So this entire pattern can be scanned 30 times per second. Okay, 30 times per second it can be scanned. So now we'll see what interactions will be taking at this point of the sample. So here we have, okay. So I'll explain this also. So here you take interaction with the sample, how the beam of electron will interact with the sample. Right. So in this case, the sample will interact with the incident electrons, which results in with separate, different types of things will happen here. So these electrons will be incidenting the sample at 90 degrees, that is normal. So with the help of this, when the incident electrons are hitting at normal, it is going to be generate the secondary electrons which are originated from the atoms of the sample. So there are certain interactions which results due to the electrons interactions between the beam, that is electron beam interaction with the sample. Secondary electrons are originated from the surface. The secondary electrons which provides the image of the sample surface. Otherwise, detailed surface information can be obtained with the help of the secondary beam of electrons which are produced. So in this, along with the secondary electrons, there are backscattered electrons, X-rays, agar electrons, and as well as some other luminescence it is going to be takes place here. So coming to this backscattered electrons, how they are producing is when an incident electron, when this incident electrons will collide normally with the atom. Here, when the incident electron beam is hitting the sample normally, some of the electrons will be backscattered nearly at 180 degrees. Right. The intensity of backscattered electrons varies with the specimen's atomic number. Hence, when backscattered electrons are collected and imaged, high atomic number elements appear brighter than the lower atomic number. Okay, this is how the backscattered electrons are going to be get. And coming to this agar electrons, how they are producing. During the emission of these secondary electrons, a lower energy electrons are released, which is leaving the vacancy into the inner shell. So the vacancy created by the lower energy electrons is filled with higher energy electrons from the same atom. The energy is released by the emission of these outer orbit electrons, which we are calling it as agar electrons we are going to be called. Okay, the release of electrons due to the emission of outer orbit electron, we will be calling it as agar electrons we are calling. Okay, these electrons are collected and sorted according to their energies, and which gives some information about the sample. And here coming to this X-rays which are producing, when the vacancy due to the emission of secondary electrons, okay, when the vacancy due to the emission of secondary electrons is filled by the fall of an electron from the higher orbit to the lower orbit. So the difference in the energy may be released as a X-rays here. The difference in the energy may be released as X-rays, which is coming out as X-rays here. And moreover, the emitted energy will have the characteristic X-rays, sorry, characteristic energy, which are from the what we call a sample. Okay, so if you take the sample preparation of this SEM, if you take, so the specimen whichever we are going to be analyzed by the electron microscope, that is with the scanning electron microscopy, it has to be dry, which mostly you'll be having the biological samples or not. Okay, so in the case of the biological samples, we cannot dry them. So the specimen which is to be analyzed by the electron microscopy has to be dry, which most biological samples are not. Okay, as dehydration might lead to structural changes, so the specimens are fixed to preserve their structure features. Okay, so first step can be achieved by using the chemical methods such as some fixation or some other methods will be there. Some physical methods also there. So like this, the specimens are then dehydrated usually by exposing them to an increasing the gradient of ethanol. Okay. And coming to the applications of this SEM, if you see, mostly with the help of the SEM, that is scanning electron microscope, we will be knowing the topography. We'll be knowing the topography. So the surface features of an object can be knowing with the help of this topography. And the samples which are in the order of nanometers, also we can be knowing the topography. So mostly with the help of the SIM, we can be knowing the topography of the specimen or sample. That is the surface features of an object we can be knowing with the help of this, and that too the sample in the range of nanometers if you are having, we can be knowing. And we can able to find out the morphology, that is the shape of the sample and size of the sample and the arrangement of the particles in making up the object we can be knowing, and we can detect some features which are limited to the order of nanometers. Okay, to the order of nanometers we can be knowing here, and we can able to find out the composition also, the composition of the sample, composition of the sample also will be knowing. That is the sample which is made up of some elements and compounds. So we'll be knowing what element it is consisting of, what type of compounds it is consisting of, we'll be knowing. And we'll be knowing the relative ratios also, means which element is having how much, we'll be knowing, that is the relative ratios. In the range of 1 micrometer in diameter, we can be knowing. And also, with the help of this with the help of this SEM, we'll be knowing the crystallographic information. Okay, we'll be knowing the crystallographic information. That is the the arrangement of atoms in the specimen and the degree of order. Okay, we'll be knowing. So mostly single crystals which are having the particles greater than 20 micrometers will be knowing. So these are the applications of the SEM we have. Okay. So then we'll be knowing about the spectrophotometer. Okay. So now we'll be knowing about the spectrophotometer. So about the spectrophotometer. Okay. If you take this the spectrophotometer is an instrument that sends electromagnetic radiation into a target and measures the resulting interactions of the energy and target. So generally this spectrophotometer uses UV or visible rays. Okay. So this UV visible spectrophotometer is which can be operate in the UV region and as well as in the visible region of the electromagnetic spectrum. And this spectrophotometer is used to measure the absorption spectra actually. Okay, absorption spectra. Absorption spectra of the substances which are in the range of around 210 to 900 nanometers. Okay, the range of this will be 210 to 900 nanometers wavelength region they can be measured. So if you see the uh, instrumentation of the spectrophotometer, so if you see the spectrophotometer instrumentation. Right. So here, this is what the single beam spectrophotometer which we have. So here the light will be entering into the instrument through an entrance slit. Okay, entrance slit. It is collimated and focused onto a what we call grating. The light of desired wavelength is selected simply by rotating the monochromator. So this is what we have, monochromator, and the light is focused onto the sample. The intensity of the radiation transmitted through the sample is measured and converted to absorptions or transmittance. Okay, so this is what actually how the light will be travels and passes onto the spectrophotometer. This is a single beam spectrophotometer which we have. And moreover, we have double beam spectrophotometers also. So in the case of the double beam spectrophotometer, here is double beam spectrophotometer. So why we use this double beam spectrophotometer is whatever may be the some limitations we have in the case of the single beam spectrophotometer. So the limitations which are there in the single beam spectrophotometer will be overcome with the help of this double beam spectrophotometer. Okay. So that is the reason why we use the double beam spectrophotometer. So mostly double beam spectrophotometer is preferred over the single beam spectrophotometer. So this is what the double beam spectrophotometer we have. So this double beam spectrophotometer will reproduce, it allows more reproducibility of measurements of any fluctuations which are happening in the light source or instrument electronic. Okay. So here we have the source here. Okay. Here we have the source, visible light source or UV light source, which is falling onto the mirror for selecting the source. Okay. So, and after that, they'll be moving onto the monochromator here. Monochromator. Then after, you have the mirrors, which we call it as a selective mirrors. And then we have the sample cell here. Like this double beam will be there and the mirror here. And finally here we'll collect the absorption or what we call transmission of the sample we'll observe here at this point. So mainly these here under this spectrophotometer, we should know about the Beers and Lambert's law. So quantitative photometric measurements of the absorption process is based on two observations. One is Lambert's law and Beers law. Okay. So if we take this Lambert's law, when when he's working on the transmission of the monochromatic light by homogeneous solid substances, he observed that the thickness of solid material played a major role in the amount of light being transmitted through that. Okay, that is what means each successive unit layer of a medium observed an equal fraction of the light passing through this. Okay, so that can be shown here in this form. This is what we have. So suppose if the incident light is having is passing through some medium, which is 1, and the medium is colored like in the form of a plastic cubes here, which are having some thicknesses. So you see the amount of it is diminished. One we got it as a 0.9. The second layer we have 0.81, that is doubled, and third layer is 0.73. So which is 0.9 and the 0.81. If you multiply, you'll get the 0.83. So the relation between the transmitted light and the light path length can be given in this form. So generally the absorption density will be given with the help of this formula, that is A log log 10 by 1 by T. This T is nothing but the transmission